The last period we
Good
have
morning.
studied about a question that we are given some value for Kc. So on the basis of that, we need to find out the other values. Yesterday, actually, we have solved this problem, but let us do a revision for this problem. The value of Kc is 4.24 at 800 Kelvin for the reaction. CO plus H2 that gives CO2 and CO plus H2O that gives CO2 and H2O. Calculate the equilibrium concentration of CO, H2, CO and H2O at calculate the equilibrium constant of CO2, H2, CO and H2O at 800 Kelvin if only CO and H2O are present initially at the concentration of 0.1 molar each. So we write first the equation that CO plus H2, it gives CO2 and H2. Then we write the initial equilibrium concentration. For CO and H2 it was 0.1 molar, 0.1 molar. But for CO2 and H2 it is 0, 0 because initially only reactants are present, products are not formed. And when the equilibrium established, let's say that X mole of each of the product be formed. So the products formed are X molar, and that is why X mole of each of the reactants have been used. So we can write 0.1 minus X molar and 0.1 minus X molar for the concentration of H2O and CO gas at equilibrium. Now we know that when we have equilibrium, we can write the equation for the equilibrium constant Kc. Therefore, Kc is equal to concentration of H2 into concentration of CO2 divided by concentration of CO and concentration of H2. The concentration of H2 and CO2 is very well we are aware that it is X molar. So we put X molar for each, and here we have mole per liter into mole per liter. For concentration of CO and H2O, we have 0.1 minus X mole per liter and 0.1 minus X mole per liter. Both have the same degree of mole per liter, and thus we can have the unit, or we do not get any particular unit. We are aware that the value of Kc is 4.24, and ultimately we write 4.24 is equal to x square divided by 0.1 minus x square. Opening this bracket, we can write 0.1 whole square into 2 into 0.1 into x plus x square, and therefore by multiplying 4.24 with this denominator, we find 4.24 is into the 0.01 minus 0.02x plus x square is equal to x square. Now we open the bracket and we write 0.0424 minus 0.848x plus 4.28 x square is equal to x square. By adding minus x square both the side, we get 0.0428 minus 0.848x plus 4.24 x square minus x square is equal to 0. For this we get the value 3.24 x square. We write the same value 0.848x and 0.0420. Now this equation is very similar to equation ax square plus bx plus c is equal to 0. So here we have a is equal to 3.24, b is equal to 0 minus 0.848 and c is equal to 0.424. We know that the root of the equation is equal to x, and if we take two roots x1 and x2, we get x is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. By putting all this value, we find that the value for x1 is equal to 0.067, but for x2 we find the value 0.194. This value is actually not possible because it is the value of concentration of products which was more than the reactants. So initially we have taken only 0.1 mole of reactants, but here if you look into the root, you will come to know that the product obtained is 1.94 molar. 0.194 molar. So this is even more than the initial concentration of reactants, and this is what it is not possible. So we consider this as a root for this equation, and we find the concentration of products. So therefore the concentration of CO2 is equal to the concentration of H2 is equal to X, that is equal to 0.0 67, and the concentration of CO is equal to the concentration of H2 is equal to 1 minus X, that is 1 minus 0.067, which gives us the 0.033 molar. So this is how we solve, or this is how we calculate the equilibrium concentration. You may be asked these questions, my dear students. Please learn these methods. Now, after revision, let us start the class today, and let's move towards the heterogeneous equilibrium. So, equilibrium in a system having more than one phase is called heterogeneous equilibrium. For example, if you look at H2O liquid and H2O gas, here we have two different phases. One is liquid, another one is gas. And this is what the equilibrium is obtained into the closed container. As we have two different phases, liquid and gas available, we call this equilibrium as a heterogeneous equilibrium. If you look at CaOH twice solid, on dissolution it gives Ca plus 2 aqueous and 2OH minus aqueous. So, but Ca plus 2 aqueous and 2OH minus aqueous, they crystallizes and form CaOH twice. This is what it is, the aqueous solution at equilibrium. We get this kind of equilibrium between the CaOH twice solid and Ca plus 2 ions and OH minus ions. Here also you can see that we have solid phase as well as aqueous phase, and thus we can say it's a heterogeneous equilibrium. Same way, if you look into the decomposition of CaCO3, we get calcium oxide solid and carbon dioxide gas. So both the solid and gaseous phase are available here, and that is why such equilibrium is known as the heterogeneous equilibrium. Concentration of solids and liquids at equilibrium are considered unity for or constant. Please remember that the concentration of solids and liquid, we consider it as a unity or unit, and that is why we write Kc for this equation as Kc is equal to for this equation we write it actually for H2O gas, for H2O liquid that has been established the equilibrium with H2O gas. So for this equilibrium, we write Kc. Kc is equal to H2O gas divided by the concentration of H2O liquid. We know that H2O liquid is 1 or constant, and that is why our Kc is equal to H2O gas. Same way, my dear students, if we write it for our second equation, that is CaOH twice solid has an equilibrium with Ca plus 2 and 2OH minus aqueous. For this equilibrium, we write Kc is equal to concentration of Ca plus 2, concentration of OH minus divided by concentration of CaOH twice, which is solid. We consider the concentration of solid either constant or unity, and that is why we put Kc is equal to the concentration of Ca plus 2 and OH minus whole square, because we get 2 OH minus, so we put square for the concentration of OH minus. Same way we can write Kp even for this. So for Kp we write partial pressure of CaO solid into the partial pressure of CO2 gas divided by the partial pressure of PCaCO3 solid. But the partial pressure of solid is almost unity or constant, and that is why we can write Kp is equal to just the partial pressure of CO2. So ultimately we can write Kp is equal to partial pressure of CO2, because the partial pressure of CaCO3 and CO is considered as a unity, or it can be considered as a constant that does not change. Now we have a question to be solved. Let's move towards that. The value of Kp for the reaction CO2 gas plus C gas, that gives twice CO gas, is 3.0 at 1000 Kelvin. If initially the concentration of CO2 or partial pressure of CO2 is 0.48 bar and partial pressure of CO is 0 bar, remember 0 bar, and the pure graphite is present, calculate the equilibrium pressure, equilibrium partial pressure for CO and CO2. Now you can look into the equation. We have CO2 plus graphite or carbon solid that gives us 2 CO gas. Here you can see that graphite is in a pure form, and that is why we do not consider it for the calculation of Kp. So initially the concentration of CO2 was 0.48 bar, and as the product has not been formed, the concentration is 0. Now, or the partial pressure is 0. Now suppose X be the amount of CO2 reacted. So X amount of CO2 has been reacted, and that is why an equilibrium has been established, and that is why the concentration of CO2 has been decreased to 0.48 minus X bar. Same way the concentration of CO has been increased. Now you can see that 1 mole of CO gives 2 mole of CO, 1 mole of CO2 gives 2 mole of CO, and that is why if X mole of CO2 is utilized, we get 2X mole of CO formed. So we write at equilibrium the partial pressure for CO gas is 2X bar. Now we can write Kp is equal to PCO whole square, because we have this stoichiometric coefficient 2. So partial pressure of Kp is equal to partial pressure of CO gas to the power 2, and the partial pressure of CO divided by the partial pressure of CO. We do not consider the solid graphite's partial pressure into the calculation. Now let's put the value for PCO. So PCO, or the partial pressure of CO, is 2X bar. So we put 2X to the power 2. And here at equilibrium, the concentration of CO2 gas is 0.48 minus X. So we write 0.48 minus X. By solving this equation using the various methods, we can find that the value of X is equal to 0.33 bar, or we can get the value of X minus. Now the value of the partial pressure can never be minus, and that is why we do not consider this negative value, but we consider this positive value for the calculation. And then, my dear students, we understand that the value of X that we get is 0.0333 bar. So we have the value of partial pressure of a CO, but the partial pressure of CO is equal to 2X, and that is why 2 multiplied by 0.33, that is 0.66 bar, and partial pressure of PCO2 is equal to 0.48 minus X, that is 0.48 minus 0.33 bar, that is what it gives us, 0.50 bar. So at equilibrium, we can calculate the concentration of the both reactant and product, that is our CO2 as well as CO. Now let's move and understand the next question. Dear students, if you are not able to understand anything, you can ask me. बच्चों, अगर कुछ पूछना है तो आप पूछ सकते हैं. ये बताने में प्लीज टाइम वेस्ट मत करें. अगर कुछ पूछना है तो पूछ लीजिए, या बोल दीजिए कि समझ में आ गया है. About the heterogeneous equilibria.
समझ में आ गया सर.
Thank you, dear. Chaliye, then let's move to the applications of the equilibrium constant. So now we want to study about the applications of the equilibrium constant. There are various applications of the equilibrium constant, but the first application is to predict the extent of reactions. That means the reaction has moved up to what extent. That is what we can determine by using the equilibrium constant. We know that our Kc is equal to the product of the concentration of reaction products and product of the concentration of reactants. If Kc is equal to 1, we can write concentration of products is equal to concentration of reactants. But if Kc is greater than, then we can say that product at equilibrium, the products are available in more concentration than the reactants. If the value of Kc is less than 1, we can say that reactants are available more than the product at equilibrium. So just by looking at the value of Kc, whether it is 1 greater than 1 or less than 1, we can easily say about the concentration of reactants and products. But this is not the mathematical way, because we do not consider, or this is just the rough idea, because we do not consider the power or the stoichiometric coefficient calculation in this way. This is rough idea because we do not consider the powers of the reactants and products. Still, we realize that using the value of Kc, we can predict the extent of reactions, because if the concentration of product is more than concentration of reactant, we can say that concentration or the reaction has been taken place more than 50%. If the concentration of if the concentration of reactant is more than the concentration of products, we can say that the reaction has been moved forward to less than 50%. At least this is what we can generally get an idea about this. So on the basis of the value of Kc, we can determine whether to what extent the reaction has been proceeded. So now if you look into this picture, you will realize that this is the forward reaction, my dear students, and this is where we represent the value of Kc. So if your value of Kc is 1, or it is between 10 to the power minus 3 to 10 to the power 3. So if your value is equal to 0.001, if the value of Kc is 0.001 to the value of Kc is 1000, you can say that both the reactants and products are present at equilibrium. So if the value of Kc is between 10 to the power minus 3 to 10 to the power 3 or 0.001 to 1000, you can say that the amount of reactants and products present at equilibrium is considerable, and they both are present at equilibrium. But if the value of Kc is more than 10 to the power 3, once again, if the value of Kc is more than 10 to the power 3, what we can say that reaction has proceeded almost to the completion, or the reaction has proceeded to the extremely large extent, and that is why the concentration of reactants present at equilibrium is negligible. Same way, my dear students, if the value of Kc is less than 10 to the power minus 3, then we can say that the concentration of reactants are available in the negligible amount at equilibrium, and reaction hardly proceed to the forward direction. Mostly the reactants are present in such equilibrium, and the products has been formed, and that is why the concentration of products when Kc is having the value less than 10 to the power minus 3, at that time the concentration of product is negligible, but mostly the reactants have been present at that particular time. So if Kc, or the value of Kc, is more than 1000, products predominate products are predominant over the reactants, and if Kc is very large, the reaction proceeds nearly to the completions. So let us look into the examples where we have the value of Kc is given, and we can come to know that these are the reactions that takes place almost for the completion. So let's have a look to this. Let us have a look the various reactions. The reaction of hydrogen with oxygen at 500 Kelvin, the value of Kc is 2.4 into 10 to the power 47. So it's a very high value, and we can say that here the reaction goes for the completion, and we get at 500 Kelvin, we get water as a product mostly. Okay, so the reaction moves in a forward direction to the great extent. At 300 Kelvin, the reaction between hydrogen and chlorine has got the value of Kc is 4.0 into 10 to the power 31. What does it mean? It simply means that at equilibrium we have mostly hydrogen chloride present. The concentration of H2 and Cl2 is negligible at equilibrium. Same way when hydrogen reacts with bromine, it produces 2 HBr, and here the value of Kc is 5.4 into 10 to the power 18. It shows that at equilibrium, mostly the concentration of HBr is present, the concentration of H2 and Br2 is negligible at the equilibrium. If the value of Kc is less than 10 to the power minus 3, my dear students, reactants predominate over the products. And if Kc is very small, the reaction proceeds rarely. And that is what we can write it, the examples that in the decomposition of H2O, in the H2 and O2 at 500 Kelvin, we can write Kc is equal to 1, or Kc dash is equal to 1 upon Kc, that is the value of Kc for this reaction. You can see that it is 2.4 into 10 to the power 47. So we take the inverse because it's just the opposite reactions, and that is why Kc is equal to 1 upon 2.4 into 10 to the power 47, which is 0.4166 into 10 to the power minus 47, which we write it 4.166 into 10 to the power minus 48. And this is how, my dear students, we can say that our Kc is having a very small value, and that is why the concentration of product is almost negligible, and mostly the reactants are present, and this reaction does not proceed. Or at this temperature, at 500 Kelvin, the decomposition of water does not take place. Same way, my dear students, when nitrogen and oxygen combines with each other to gives us a 2NO gas, the Kc for this is 4.8 to the 10 to the power minus 31. That means nitrogen and oxygen, when they combine at 298 Kelvin, that is your 25 degrees centigrade temperature, they generally do not form nitric oxide NO, because the reaction is because at equilibrium, when the equilibrium is formed in this reaction, there is no product, or the concentration of product obtained is negligible. If Kc is in the range of 10 to the power minus 3 to 10 to the power 3, appreciable concentration of both reactants and products are present. So if the value of Kc is in between the range of 10 to the power minus 3 to 10 to the power 3, we can say that at equilibrium both the reactants and products are available, and their concentration is not negligible, but their concentration is considerable. So for the reaction of hydrogen with iodine, Hi, Kc is 57. That means it follows in the range of 0.001 to 1000, and that is why when N2, so when Hi is formed from H2 and I2, H2 plus I2, that gives Hi, 2Hi actually. So in this reaction, if we really look into that, at equilibrium, both the hydrogen and iodine and the hydrogen iodide, all three are present. Same way, when N2 for decomposed to gives 2NO2, the Kc for this 4.64 into 10 to the power minus 3 at 25 degrees centigrade, and this is how we can say that at equilibrium the concentration of both the reactants and products is available to the considerable amount. Same way, my dear students, when so we should find out a proper method to predicting the, now we can look into the next application of our equilibrium constant, and the next application is the predicting the direction of the reaction. So if we are given the value of a constant, then can we determine whether it is or it will move into the forward direction, reverse direction, or backward direction, or it is at equilibrium. So to predict the direction of the reaction, we need to determine or calculate the reaction quotient, which is known as Q. So reaction quotient, your reaction quotient Q, the reaction quotient Q or QC with molar concentration QP with the partial pressure. So we need to find out first the reaction quotient. Reaction quotient is called QC when we have the molar concentration of reactants and products, and we call it QP if we have the partial pressure of reactants and products available. Now, how do we define it? So the reaction quotient Q or QC or QP is defined in the same way as the equilibrium constant Kc is defined, but there is an exception. What is the exception? Except that the concentration of in QC are not necessarily the equilibrium values. So when we calculate QC, or when we take the ratio of the uh, um, uh, concentration of products to the power raised equal to their stoichiometric coefficient divided by the concentration of reactant to the power raised to them is equal to their stoichiometric coefficient. This is what it is known as our QC. But remember that we do not consider the concentration which are available at equilibrium. So at any phase or at any time of the reaction, which is generally not the concentration, which is not the equilibrium time. So at any time other than the equilibrium time, if we take this concentration ratio according to the law of mass action, then this value is known as QC rather than the equilibrium constant Kc or Kp. So the basic difference between the calculation of QC and Kc is that at Kc we consider only the equilibrium concentration, but in QC we generally use the values of the concentration of reactants and products other than the equilibrium concentration. Now we compare this QC with KC. So if the value of QC is greater than KC, then the reaction will proceed in the direction or towards the in the direction of reactants. That means the reverse reaction takes place. If the value of QC is greater than KC, so think of, suppose we have Kc here, so this value is greater than Kc. That means the concentration of product is more than the concentration of product is more than the concentration that can be available at equilibrium. But we know that the reaction will always move towards the equilibrium, and that is why the concentration of reactant should be decreased to obtain the equilibrium, and that is why the reverse reaction takes place. So my dear students, please remember that if the value of QC is greater than KC, then the reverse reaction takes place. Let's move forward. If the value of QC is less than KC, sorry, I think if the value of QC is greater than KC, then the reverse reaction takes place. If I have mistaken, please consider it. And if the value of QC is less than Kc, then the reaction will proceed in the direction of the products, and we will get the forward reaction takes place. But my dear students, if the value of QC is equal to Kc, actually it represents the equilibrium situation, and then we can say that the reaction need not to move in any direction. So if QC is equal to Kc, then the reaction mixture is at equilibrium, and it does not move in either the forward or backward reaction. Both the reactions are going on at the same pace or with the same rate. To understand the same, we have a graphical representation. You can see that with the green color we have represented QC, and with the blue color we have represented KC. So if the value of QC is less than Kc, then we can say that the reactants are less than the reaction will move into the forward reaction. If the value of QC and Kc are equal, we can say that reactants and products are at equilibrium. But if the value of QC is greater than Kc, we can say that the reaction moves from the products to the reactants, and the reverse reaction takes place. So here we can say that when QC is less than Kc, we can say it's a forward direction, and when QC is greater than Kc, we can say it is the reverse reactions that is possible. I think I have written it with the pen, with the red color pen. It's clearly that QC is less than Kc, it shows the forward direction. When QC is equal to Kc, it shows the equilibrium. And when QC is greater than Kc, we can say that the reverse direction takes place. So now the same thing we should understand by solving some of the problems. So let's look at the question. The value of Kc for the reaction 2A is at equilibrium B plus C is given, and the value of Kc is 2 into 10 to the power minus 3 at given time. The composition of a reaction mixture is the concentration of A is equal to the concentration of B is equal to the concentration of C is equal to 3 into 10 to the power minus 4 mole per liter. In which direction the reaction will proceed? So they have given us Kc. We just need to find out the Qc. We are given the reaction 2A that gives us the B plus C. So our products are B and C, and reactant is 2A, and that's why we write QC is equal to the concentration of B into concentration of C divided by concentration of A to the power 2, because we just need to use power because the stoichiometric coefficient for A is 2. Now by putting the value, the concentration of A is equal to B is equal to C is equal to 3 into 10 to the power minus 4 mole per liter. So we put 3 into 10 to the power minus 4, 3 into 10 to the power minus 4, 3 into 10 to the power minus 4 for all of them, but for A we need to put power. We know that here the unit for the denominator and numerator will be molar square, and that is why the value of QC will be unitless, and we get the value of QC is equal to 1. 1 is greater than 3 into 10 to the power minus 4. Please remember that we are given the value of Kc, and the value of Kc is 2 into 10 to the power minus 3. I made a mistake. It's a 2 into, or 1 is greater than 2 into 10 to the power minus 3. So the value of Qc is greater than the value of Kc. As the value of Qc is greater than the value of Kc, what we understand simply is that the reaction will go into the, can you tell me in what direction the reaction will go? Here the value of Qc is greater than Kc. Here the value of Qc is greater than Kc. In what direction it should go? Dear students, I am asking you, the value of Qc is greater than Kc. In what direction the reaction should go? बच्चों आप मुझे नहीं सुन पा रहे हैं?
Right to left.
Yes, that means what kind of reaction do we call it?
Reverse direction.
Very good. It moves into the reverse direction or the backward reactions. That is what we can predict. So this is how, so the reaction will proceed in the reverse directions. Let's solve one more problem to understand it better. 13.8 gram of N2O4 was placed in 1 liter reaction vessel at 400 Kelvin and allowed to attain the equilibrium. You can see that the equilibrium is established as N2O4 gas. At equilibrium, we have 2 NO2 gas. Now, the total pressure at equilibrium was found to be 9.15 bar. Calculate Kp and Kc and the partial pressure at equilibrium. So please remember that we have the decomposition of N2O4 into 2NO2. So yeah, here the mass of the N2O4 is given, the volume is given as 1 liter, the temperature is 400 Kelvin, the total pressure given as a 9.15 bar, and we need to find out the value of Kp and Kc and then the concentration. So here mass given, molecular weight of N2O4, we find out it is 92 gram per mole. We know that number of mole is equal to given mass divided by the molecular weight. So given mass is 13.8 and the molecular weight is 92, and therefore we get the number of mole is equal to 0.15. So now, my dear students, we have the mass, the value of mole is equal to 0.15. We know that our value of R is equal to 8.314. We can write it 0.02 liter into atmosphere, but to calculate the Kp, we need the value in bar, and that is why we take it 0.083. The temperature is given 400 Kelvin. So using the ideal gas equation, we write PV is equal to nRT, and therefore P is equal to N by V RT. This N by V RT will, and therefore N is equal to 0.15, R is 0.083, the temperature is 400 Kelvin and volume is 1 liter, and thus we get the partial pressure, and that is what partial pressure for N2O4, because partial pressure for N2O4 is 4.98 bar. So when this N2O4 decomposes to gives us twice NO2, the initial partial pressure is 4.98 bar. That is what we can understand. Now, my dear students, we want to move forward and understand this. So let us write the equilibrium N2O4 that gives 2 NO2. Initially, we have just calculated the total pressure of our N2O4 was 4.98 bar, and the product has not been formed. If X mole of this is used, if 1 mole of this is completely used, we get 2 mole of it. So if X mole of this N2O4 is used, we will get 2X mole or 2X bar of NO2. And suppose X mole of this or X bar of this is being utilized. So the partial pressure of N2O4 is decreased by X, but the partial pressure of NO2 is increased by 2X. So now if we want to write the total pressure exerted by both these reactants and products at equilibrium, so that pressure exerted by N2O4 is 4.98 plus X. The pressure exerted by NO2 is 2X bar, and that is why the total pressure at equilibrium, please remember, at equilibrium the total pressure is equal to 4.98 minus X plus 2x, which simply gives us the value 4.98 plus x. But in the question, they have given us the value for total pressure, that they have clearly mentioned that the total pressure at equilibrium, my dear students, the total pressure at equilibrium is 9.15 bar. So let us put the value that 4.98 plus x is equal to 9.15 bar, and that is why the value of x is equal to 4.17 bar. So now we put the value 4.98 minus x is equal to 4.98 minus 4.17, which is equal to 0.81 bar. Same way, if you write it for 2x bar, we write 2 into 4.17, that is 8.34 bar. So this is how, my dear students, we calculate the equilibrium concentration for the reactants as well as the products. Now putting those values, we can find out Kp. So Kp is equal to partial pressure of NO2 to the power 2 divided by partial pressure of N2O4. By putting the values, we get Kp is equal to 85.87 bar. Same way, my dear students, for N2O4 minus 2NO2, the number of gaseous mole of product is 2, number of gaseous mole of reactant is 1, and that is why delta N gas is 1. So by using the equation Kp is equal to Kc into RT raised to delta N, where delta N is equal to 1, we write Kc is equal to Kp divided by RT to the power 1. We know the value of R, we know the value of T, and then by putting all these value, we even find out the value for Kc, and we do not forget to write the units. So this is how, my dear students, we can easily understand the calculation of Kp, Kc and equilibrium concentration for all the reactants and products, my dear students, and we understand this idea very well. Let's look into the third question. 3 mole of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin. Calculate the composition of the mixture at equilibrium, and your value Kc is equal to 1.80. Now you can see that 3 mole of PCl5 is kept in 1 liter. That means it's 3 mole per liter. That is what we can understand the concentration. And that is why initially we have 3 mole per liter, that is 3 molar concentration of PCl5, which is decomposed into PCl3 and Cl2. Let us say X mole of PCl5 is used up during when the equilibrium is established. So the concentration of PCl3 is going to be X mole, concentration of Cl2 will be X mole, and X mole of PCl5 as it is utilized, we can write 3 minus X molar. Now by putting all these values into the value of Kc, we can find Kc is equal to concentration of PCl3, which is X, the concentration of Cl2, which is X, and concentration of PCl5 is equal to 3 minus X, and the value of Kc is given 1.80. So by solving this equation, we find out the value for our X, and that is what the negative value for X is not considered, and the value of X is considered as a 1.59 molar, and that is why the concentration of PCl3 and concentration of Cl2 is 1.59 molar, whereas the concentration of PCl5 is 3 minus X, that is 3 minus 1.59 molar, that is 1.41 molar. So my dear students, here we have discussed the enough number of problems of regarding Kp, Kc and finding out the equilibrium concentration. Please learn this. And in the next period, we will study about the relationship between the equilibrium constant K, reaction quotient Q, and the Gibbs free energy G. So you can revise these topics from your textbook or from the notes which I have given. Please be prepared in advance in the class. And now if you have any doubt, you can ask me. बच्चों अगर आपको कुछ पूछना है तो आप लोग पूछ सकते हैं.